study of the amount of time it takes a mechanic to rebuild the transmission for a 2005 Chevrolet Cavalier shows that the mean is 8.4 hours and the standard deviation is 1.8 hours. If 25 mechanics are randomly selected, find the probability that their mean rebuild time is less than 8.7 hours. Solve the problem, round to the nearest tenth unless indicated otherwise. Okay, so this question is regarding the time to rebuild transmission, so that's the random variable, and its mean value is 8.4 and the standard deviation is 1.8. However, the strange thing is I don't see anything like normally distributed or bell curve, bell-shaped distribution. None of that is appearing, so it doesn't look like it's a normal distribution. But on the other hand, it doesn't have any probability for individual things, so it's not binomial distribution. So you start wondering, what is this? Okay, and the hint is right here, the word mean. And if you look at this again, it's the mean value of a sample, right? And the sample size is 25. There n equals to 25 sample size, and we're looking for the mean value. And that mean of a sample size has a slightly different distribution than the original x, original random variable. And it's very, very important that you remember this formula, which is the standard deviation of a sample mean is given by the following formula. You have to divide by the original standard deviation and by the square root of the n. And if we compute this, we get 0.36 by use of a calculator. And the beautiful thing here is that there is a mathematical theorem called central limit theorem that once your sample size grows, usually people call for 30 or more, but 25 is still enough. If the original is somewhat normally distributed, then 25 could be enough. And if that happens, then the sample mean is normally distributed, even if the original one is not normally distributed. That's the central limit theorem. With the standard deviation 0.36 with this formula right here, the mean value is same as the original one. So the original mean just carries over. The standard deviation, however, has to be divided by the square root of n. And now we can use the normal curve still because the central limit theorem says so. Okay, so this is another type of normal distribution problem where you're not given the word normal distribution, but just the fact that there's the mean value of some sample, we can use the standard normal distribution or the normal distribution. Okay, all right, so let's carry on. Once we know that the x bar follows a normal distribution of 8.4 and 0.36, then we can happily use all the formulas that we know about normal distribution, right? Specifically, in our case, we want to know the probability that the mean value is less than 8.7. So it's the probability of x being less than 8.7. By the way, I should have said strictly less, but you know, in a continuous random distribution, just continuous probability distribution like the normal distribution, whether you have a strict inequality or containing, it doesn't matter. Okay, so strictly less than or equal to doesn't really change the value of p because we're playing with the normal distribution. If this was a binomial distribution, which is discrete, it would have some different consequences. Okay, all right, so we use the usual z-score, subtract the mean value and divide by the sigma, but remember the sigma here is this one. Okay, so we're just completely forgetting the first part where we came up with this result, and now we're pretending if all we know is 8.4 and 0.36. So I'm going to use those values and get the value 0.8333. And now this probability translates to this probability, okay? Because 8.7 is now changed to z-score as 0.8333. So saying that x bar is less or equal to 8.7 is same thing as the probability that z is less or equal to 0.8333. Let's draw the bell curve. Here's the standard normal distribution, and here's the 0.8333, and because you're looking for the z left of this point, we have to shade this left side. And once you shaved, you can say that the probability of this, or the area under this curve, is given by this normal CDF function from the calculator. So let's turn the calculator on. Second vars normal CDF. Remember, always for the normal distribution, you use the CDF, not the PDF. And binomial, you usually use PDF, but sometimes CDF is also used. Okay, now we don't change the lower or the 0 or 1. Everything is kept as it is, and we only change this one. I'll clear it and then put 0.8333. Enter, enter, and you get 0.7977 if you round it to the to that, and then so you get this as your answer, and because rounds the nearest tenth, I guess you put this as 8. Okay, so 79.8% chance that the mean revealed time is less than 8.7. Now, sometimes some teachers do not allow the use of these things, and they make you use the table, the normal distribution table. You have to know how to read it, and if you look at 0.83, right, this is 0.03 more than this value here, 0.8, so 0.83 has the value of 0.7967. Also, if you round it to the nearest tenth, that's 79.7%, so you get the same answer that way as well.